So we'll work on the section 1.4.4 now, and we'll learn about what is band sharpening first, and then how to apply this on our Lancet data, that if you have one band at 15-meter resolution, we have other bands at 30-meter resolution, can we improve the resolution? And we'll see how GDAL can do that. If you look at any multispectral sensor and see what is the length, the different bands and their wavelengths, you'll see something similar to this. This is for Lancet 8, the one in the red box. You can see the band 2 is the blue band, band 3 is the green band, band 4 is the red band. So each individual band is sensitive to a very small range of wavelength. And when you are trying to detect light in the very small, narrow wavelength, you have to design a sensor that can collect more light. So a sensor has to collect more light, so it needs to look at larger area. If it's trying to look at smaller area, you won't have enough signal because your channel is so small. You have very less light and you'll get a lot of noise. So to overcome the signal to noise ratio, you have to design your bands so that they are, if your band size is small, your resolution has to be bigger. That's just the fundamental physics. So what a lot of the satellite sensors do is they have this red, green, and blue bands, which are narrow. They'll put a larger band, which says this is sensitive to all the visible light. Similar to a black and white camera. If you remember the old black and white film cameras, if you take a photo, they are sensitive to all visible light. So you have a much larger field of wavelength that you are sensitive to, and you can design this to detect smaller things. So typically the pan band, which is panchromatic means across all the visible spectrum, panchromatic bands have a higher resolution. If you look at most sensors, they look like this. This is the table showing the difference in resolution between the pan band and the RGB band from most common satellites. Lancet 8 is 15 meters, 30 meters. So you have RGB data collected at 30 meter, pan data collected at 15 meter. If you look at the SkySat data, you have 75 centimeter resolution for RGB, 60 centimeter for panchromatic. The highest resolution since commercial satellites, they have much larger difference. So you can see WorldView 2, 1.8 meter, almost 2 meters of RGB data and 50 centimeters of pan data. If you go and order something from Maxar and say, I want some WorldView 2 data, they will give you an option. Do you want data at 50 centimeter RGB or you want 1.8 meter RGB? And you would say, oh, I definitely want 50 centimeter. And they will say, okay, buy the pan sharpened product from us and we'll charge you more money, but we'll give you better product. They don't have any data at this resolution. They have only pan information. The RGB information is only at this resolution. What they do is they apply some pan sharpening algorithm, which will improve the resolution from this using the information contained in the pan. Okay? So we're going to learn how this process works and how you can do this using GDAL. So next time you're ordering imagery, you say you pay X dollars for RGB and 2X dollars for pan sharper RGB. You can say, I'll save my X dollars, I'll do the pan sharpening myself using GDAL, and I just give me the raw bands. There are many ways to do this. Most famous algorithm is called Brovie algorithm. That's what GDAL uses. We'll learn about that. There's also an algorithm called IHS transform, which uses the RGB to HSV space transformation. Earth Engine, if you're using Earth Engine, it uses this. Many remote sensing software also have an option to do this kind of pan sharpening. And there are other methods that use wavelet methods or PCA methods. So some of you may use this. We're going to focus on Brovie. I'm just going to explain that since GDAL supports only Brovie method, but I have linked to a paper and the end of the slides if you want to see the comparison between different things. And again, you'll have software that can support different options. The Brovie algorithm is very simple. It says, I have more information in the pan bands. Can I take the ratio of the pan band intensity at each pixel and apply that to each RGB values? And I can use this. This is the formula, but just much clearer if you just do this visually. So I'll just explain that visually. So let's say we have this large pixel. This is your Lancet 8 pixel, red, green, blue. The value of the pixel is 15. That's the intensity value. And we learned that the pan band has twice the number of pixels, right? It's just half the size. So this is what the pan band would look like. It says, oh, the RGB sensors could only detect one value at this region, it was 15. But there's a lot more information that is there in the pan band. You can see there's a lot more variation here, but this bands could be correct. Can we improve the resolution of this RGB channels using this information? So the Brovie algorithm, first, we'll say we'll just resample our original pixel values, divide into 4 pixels. So we have the same match. So we have each pixel value, and we can do this. So you can see if you just simply resample it, the pixel value remain the same. You don't have any new information yet. Now you can say you have this 4 values here. At each pixel, we have some red, green, and blue. If they were combined equally using the pan channel, you can say pan channel is detecting light in red, green, and blue, it would be 15, but it's 10. So there is something else going on. There's information that is not equally divided among red, green, and blue. So you can say we'll apply this thing that if it was red, green, and blue equally, it was 15. If it's pan, says 10. So the proportion of light for each thing is 10 divided by 15, 10 divided by 15, and 10 divided by 15. And you multiply that by each value, and you get your sharpened value where each pixel is now changed in the proportion of the original pixel values. So now you can see I had this only information about this pixel as 15. Now I can say, oh, actually this contains more information. On the whole, average is 15, but inside there's more information, which I got based on the information that was contained in the pan band. I could sharpen this. And again, you will see your image improve in the resolution. You can resolve roads or other buildings much nicely because that information was contained in one band. You could sharpen your RGB bands and improve that. This kind of thing is useful mainly for mapping, where you're saying, I'm trying to map this, I'm trying to draw this road on this image. I can't see it clearly. I can sharpen that and I can see the roads more clearly. So pan sharpening is mainly used for mapping. It's not used for analysis. If you're computing NDVI or other things, typically people don't do this because this is actually the scientific observation. This is more like an approximation that we did on a pan band. So when you get this, this will be an approximation. So for scientific analysis, use the raw values. For creating a product for mapping or for visual purposes, you can apply the pan sharpening. The more modern approach to this, what you see is super resolution, which you can build an AI model which says, I know where if the big pixel is like this at this location, small pixel looks like this. I'll give you this big pixel. Can you predict what is the small pixel? I don't have any information. I can predict. That is the super resolution information. A lot of the commercial data providers are now doing this, where they say, if you go to Maxar, their commercial satellite is now 30-meter resolution. They are selling a 15-centimeter product from 30 centimeter using super resolution. So they said we can go from 30 centimeter to 15 centimeter by using the CNN-based super resolution technique. A lot of these are again based on raw training data for a very specific region, but this is not that. This is a technique for improving the resolution of the data from the same sensor collected at the same time. I've linked to some resources. This is a HSV transform from Earth Engine. You can look at that. This is some other wavelet transforms. If you want to learn more about what those are. These are more classical remote sensing methods. So we're studied in a textbook. And again, every provider will have to do something this before they share the data with you. So let's learn how to process this raw data using the GDAL pan sharpen tool. So this is your GDAL pan sharpen tool. The documentation for that says GDAL pan sharpen. You have two things here, pan dataset. So what is the band containing the pan information? Spectral dataset. So where is your RGB? You can give multi-band RGB or each band separately. So you say this is my pan band, this is my RGB, and you have some options and it'll just create an output. So you can say pan, RGB, output, and then some options. This is how the pan sharpen algorithm works. Let's apply this. You can go to section 1.4.4 and copy this command. Let's run it, and I'm going to explain this to you. We're going to run this in the Lancet 8 folder. So we are in the Lancet 8 folder. We have the RGB TIFF that we have created. Here we have the bands. We have the RGB.TIFF containing the red, green, and blue channels. We have the band 8, which is the pan band. So the GDAL pan sharpen command says, take the band 8. So this is the band 8 value. That's your sharp band, your pan band. RGB TIFF is what we want to sharpen. So take the RGB raw observation at 30 meter, make it 15 meter. And we'll create a new file called pan-sharpen.tiff. While you're pan sharpening, there is some interpolation going on. So we can say use the bilinear resampling and apply a compression as usual. Let's just run this. And at each pixel, it is doing this. It's taking the RGB pixel values, pan values, creating the proportion of RGB into the pan value and rescaling those values. to give you pixel at a higher resolution. This is the first command in the section 1.4.4. Use the appropriate command for your platform. If you're on Windows, use this one. If you're on Mac, use this one. Have the pan sharpen.tiff. Again, this image has the same problem. We've sharpened it, but the contrast is still very low. So we can apply the same contrast stretch that we applied to RGB, so you can visually see the difference between those two. So once this command finishes, you can run the next command, which is applying the same scaling. So take the raw values from 0 to 0.3, apply the stretch from 0 to 255, and with the exponent of 0.5. So run the next command as well once this command finishes, and you'll get this pan sharpen stretch image. And this will just allow you to see the result in a much more higher contrast, so you can compare those results. So I want you to load the RGB stretch image and then pan sharpen stretch image. So go and load the RGB stretch image that we had created in the previous section, and then the pan sharpen stretch image. And just go and look at the imagery. See what the raw and pan sharpen versions look like. And you could see the improvement in the resolution. So you can compare the RGB stretch, which was just the raw band at 30-meter resolution, the pan sharpened one, the ones that we improved the resolution using the information in the pan channel. So where this might be useful? Well, things like if you are using your imagery for deep learning and you're trying to detect cars or buildings, and you're trying to do this on RGB, you can't really see the edges of the buildings or roads clearly. If you do pan sharpening, you'll see them more clearly, and your algorithm will be able to delineate them well. So again, if you want to improve the visual appearance of your imagery, pan sharpening is useful, typically used for mapping and doing object detection on satellite imagery.